This is Computer Networks Chapter 1, Part 3, in which we look at queuing theory, tools, and internet service providers, and a little internet history. In a packet-switched store and forward network, the arrival of a packet has to be stored somewhere before it can be forwarded on. Ultimately, we're going to store these received packets in a queue. Despite the fact that the arrival and potential departure of a packet seem like they are random events, operational research, a branch of mathematics, has developed math models that describe the characteristics of a queue and the system around it. We can represent the arrival rate of packets in packets per second. We can represent the bit rate for each packet, and we can represent the length of each message. And we can then use that to compute the arrival rate ratio. Notice that the ratio is unitless. In other words, all of the units cancel out. And as a result, this is just some expression of the relationship between these quantities. When this ratio is less than 1, we can say that the system is in steady state. And while there can be bursts of traffic, there will also be periods where there's no new packets arriving, and this is going to be governed by the randomness of that system. A system that's in a steady state will gracefully handle the load, and while it might get bogged down once in a while, it will also eventually return to an average humming along state where everything is able to be handled. In other words, in a steady state system, the queue delay will have a finite maximum value. On the other hand, when the ratio exceeds 1, we have this weird situation where packets are arriving faster than they can be queued up, and the incoming packets will have to be dropped. You can imagine this like a leaky bucket, where you're pouring water into the bucket and there's a number of holes in the bottom where water can flow back out of the bucket. But if you're pouring water in faster than water can flow out, eventually that bucket is going to fill, and then it's going to slop over the top, and water will be lost. So we can use this arrival rate ratio to calculate other factors as well, such as the average length of the queue. And we can use that property to size the network device's characteristics. For example, if I know that I'm going to have, based on the usage pattern, I need to have deeper queues, I can use that to find a vendor that has equipment that has larger memory queues available to it. Or we could just plan for additional routes for packets to follow so I can forward on multiple links, and all kinds of different strategies that we can do. So this one simple ratio is actually really quite important to perform. And if you remember the formula for this, it was AL over R. Now, a lot of times when you get these figures, we have to be really careful about mixing bits and bytes together. So in this example, we have exactly that happening. We have the length given to us as bytes, whereas the arrival rate or the transmission rate is given to us in megabits. So when we go to solve this equation, we have to pay attention to that. The standard conversion to convert bits and bytes, I think we may have mentioned this before, but we'll say it again, is going to be 10 bits for most networks. And again, that's because of this thing called 8B, 10B encoding. It also just happens to make the math a little bit easier. Now, 8B, 10B is not the only strategy. There are some networks that use 12 bits per byte. Some networks actually will add additional bits of like preamble and postamble to a network packet. We're going to simplify all of that. Unless it's given to you, assume 10 bits per byte. So if that's the case, what we can do now is we can set up our formula. So we have our arrival rates as 5,000 packets per second. And we're going to multiply that by, and I guess there's an implied units here of 1,500 bytes per packet. So if we do 1,500 bytes per packet, we can see the packets cancel. We now have bytes per second, but we need to get this into bits per second, and so I'll get the 1 byte down here to cancel by using 10 bits. So the bytes cancel, and now I can use my last term, which is going to be our R. And remember, R is megabits per second, which we could really say is megabits per second as a fraction. And so I'd want to get that second in the numerator, and so this gives me 500 million, or 500 times 10 to the 6 bits. So now I have seconds canceling, and I have bits canceling. And this is why we say arrival rate is unitless. So now we can go ahead and calculate. I have 500 5,000 times 1,500 times 10 in the numerator is 75 million times 10 to the 6. And in the denominator I have 500 times 10 to the 6. So now it's really easy to do in my calculator. If I really wanted to, I guess I could do the division the old-fashioned way, and I get my 0.15. So our arrival rate is 0.15. Could also have gotten there just by saying 75 divided by 500, because the powers of 10 here canceled out. Alright, so the last question we have to ask is, if this number is less than or equal to 1, then we are in steady state. If it's greater than 1, we are not in steady state. And in this case, we are going steady. And so this particular queuing system should be able to handle this load and actually be idle most of the time. So that's how you do these arrival rate ratio calculations. I think the biggest trick that you're going to encounter, and I'm going to say it one more time, is if someone tells you bytes, that's kind of how we always talk about packet sizes, but then we also are almost always giving rates in bits per second. Could I make it easier? Oh, there's a rainbow color. Could I make it easier on you, and could I give you the rates in bytes per second? Sure, but I won't. That's just not how we do it for whatever reason. In a network, as we look at each of the different types of delays, we had seen from the last lecture things like the processing delay, the queuing delay, transmission delay, and propagation delay all added together to become the total nodal delay. As we add nodes in a packet switched networks, it turns out that those delays are also additive. Every device along the way will store and forward the packet, and each will add its own delay. In a simple network, if a network device is overwhelmed, there's nothing to do other than wait, and those delays start to skyrocket. In a complicated network with multiple paths to the same destination, as the delays start to add up on one link, maybe we can start picking differing routes and use less loaded routes that may have less traffic on them, and thus less delay, and they can handle our data more gracefully. In fact, it's possible that in a large, complicated network, as messages are sent through the network, every different packet could actually be sent along a different route and even arrive at the receiver out of order. If I send 3 packets out to a remote device and the first packet hits some congestion, the second packet might go to another link that also has some congestion, and the third packet might get routed to a link that has no congestion at all. The third packet might arrive, then the first packet might arrive, and the second packet might arrive. And so we have to be able to reassemble those on the receiver. This is also one reason why sometimes your internet can be down, where some services, usually the ones that you don't care about, are up and fine, while others, such as like getting out to the Steam cloud or getting to Google, are just down or very slow. One tool that you can use to try to figure out, is my internet down, or is it just the links that I'm using to get to that site, or maybe it's just that one site is down. One tool that we can use is called the Traceroute utility, and that will be able to show us the path through the network. And I'll have a demo of that coming up shortly. There are three main ways of analyzing network delays. We can do it using real-world tools such as Traceroute, Wireshark, or other system utilities or devices. We can also do it mathematically, where we can generate a mathematical model to model the system, or we can do it through network simulation. Real-world analysis uses analysis tools to assess the actual performance of a system right now. Information in the real world is typically the most accurate, but because it's real and the internet is constantly changing paths as links become hot or cold or even going down completely, real-world analysis is also, in many cases, the most difficult to obtain and analyze and contains the least accurate picture of what will happen in the future and provides very little information about what could possibly happen. On the other hand, mathematical analysis, often using tools such as MATLAB, are excellent for modeling specific scenarios. But it can be very difficult to model real-world behaviors in these tools. For example, modeling the actual behavior of a specific application, such as a web browser surfing pages, versus, say, modeling how a user watching Netflix can stream a movie, that can be very difficult. On the other hand, we can derive a precise mathematical model of the system, and we can even then use that model to do extrema analysis, to determine maximum theoretical loads or find bottlenecks before those loads actually happen. So for example, if we took the time to build a very accurate model, we could, in theory, be Netflix, and we could ask the question, well, what happens if 10,000 users try to watch the same movie at the same time? And we could then determine how do we best meet that load. Finally, we can use an application-specific network simulator such as Cisco's Packet Tracer to model real-world devices and protocols. With tools like Packet Tracer, we can get really close to real-world accuracy and still push a network to its limits. But we lack access to the underlying mathematical models and are therefore somewhat limited in what we can learn from the simulation. On the other hand, tools like Packet Tracer allow an engineering model to represent a problem that we actually face. We can recreate some kind of failure in a network, or we can recreate some network load that's kind of atypical. And then we can work on designing a fix and implementing it in Packet Tracer and determine that the fix actually fixes the problem before we try to deploy it into a larger network. We can even use it to do automated tests where we can then make sure that our fix doesn't actually break something else. And given the billions and hundreds of billions of dollars that are invested in network technology, being able to know that you're not going to blow out a network somewhere else to fix this problem is a really valuable thing for an engineer. So let's take a look at some real-world tools. We'll take a look at Wireshark and Traceroute.
Okay, I wanted to do a quick demonstration of using a couple of tools just to kind of show you how some of this stuff works. One of the tools that we talked about packet switching networks is using Traceroute. Traceroute's available in both Windows and Unix systems. The name of the command changes in Windows. It's TraceRT. But anyway, so Traceroute, if I were to go to a place like google.com, what we can see here is a list of routes that my packets are taking. And as we kind of interpret this, we see that we're kind of on, this is from campus. I'm going from Sloop directly to our port on the campus router through some internal networks, out the campus router called gate, kind of cute. A couple of hops along the SHENET, the State System of Higher Education network, and then that gets me to Washington, D.C. L3. I go through L3's internal network and get to Google, and all of this stuff from now on is through Google's network until they respond. And along the way, we can see, for example, that there was a 1 millisecond nodal delay from Sloop to our route to our side of the router. There was a 4 millisecond delay to get to the internal network, 5 to gate, another 5. But then we start getting into some bigger jumps. So we also see that it's not monotonically increasing. So for example, here we have 22 milliseconds to get to Washington L3, but then it's 15 milliseconds to get to the Google side. It's just that when this ping was taken, that's how long it took. If I ran this again and compare the differences, we may even see a different path this time, and we certainly may see different times. And in fact, we do see a different path, and we do see different times. So this is just kind of showing the reality of how packets are moving through the network. When you see these stars, these aren't errors, but rather these are hosts that do not advertise themselves. And this may be for security reasons. If you don't want a host to advertise that it exists, it can still handle traffic. It just isn't going to tell you who it is or where it is. Let me go to a different website. Let's try to go to ubuntu.com. And here we see far fewer hops. Okay, so this next program I want to show is something called Wireshark. Wireshark is a utility that we can use to sniff network traffic that's showing up on a particular network card. This is my machine, my personal machine, and I have 2 Ethernet adapters that are built into it. One of them is not plugged in, but the other one is. It has a heartbeat here. These are some virtual network adapters. For instance, this is what we use with WSL, the Windows Services for Linux. It has its own virtual network. VMware likes to throw in a bunch of different virtual network connections for each of the virtual machines. I'm going to go ahead and just pick the active Ethernet adapter. And when I do, we'll see kind of a steady stream of datagrams arriving on my network card. So what we can do, we'll just kind of capture a few of these, and I'll go ahead and hit stop. What this is going to show is it shows a couple of really interesting things. And later on in this lecture, we're going to talk about the protocol layers. And every time I look at one of these are a packet of data, and we can see that there is just the different layers of things that are kind of built into this. So whatever this packet is or represents, at the top layer, or the bottommost layer really, is what came off of the Ethernet card itself. So the Ethernet device driver said, here's a gob of data that's 2,896 bits wide. It actually was 362 bytes on the wire, so there was some encoding differences between the two. It was an Ethernet 2 frame. Ethernet is, of course, what we've been talking about before, and we can see here that it is a destination of that MAC address. It had a source of this MAC address, and it had a type of that. Whatever that type is. So that's just what it's telling us. It decoded that to be IP version 4. After the Ethernet envelope, there was an IP protocol, and it has all of this kind of crazy information. And then this IP protocol says, hey, this is a user datagram protocol. And then we have some data embedded into there.
Here we can take a look at building a very simple network model in the SIM events tool within MATLAB.
So this demonstration is using MATLAB and the SIM events tool to model a simple network. So to get started, what I want to do is start SIM events, and I can do that just by typing in SIM events from the MATLAB command window. This will bring up a model library, and this contains each of the different basic types of things that we can use in the SIM events system. SIM events is not network specific, it represents anything, and so in this case we're going to use, for instance, entities that just represent generic things, we're going to use them to represent network packets. So to get started, what I'm going to do is I'm going to make a new model. I'm going to move this over here just to kind of get it out of my way. And I'm going to add that network or that entity generator, and again, we'll make this represent network packets. There's the queue. Here's our entity server, and we'll throw in our terminator. Alright, so I'm really done with the library, so we'll put that out of our way. What I want to do next is I just want to go ahead and connect these guys. And to make sure that everything works, we'll go ahead and hit run. And nothing major here is really going to happen. Okay, so it ran. Yay. I might be interested, though, in seeing some statistics. And get those. I can turn on statistics, and so if I want to see the number of entities that were departed or the average waiting time might be really interesting. The average queue length is also something that we're often interested in. And so what I want to be able to do next is to include Simulink library. Alright, so the Simulink library has a lot of things going on here. And what I'm really interested in is going to be here under syncs. I want to be able to see the actually, maybe we'll do an oscilloscope view. So let me add an oscilloscope that's going to have our queue length, and we'll have another oscilloscope view that's going to have our waiting time. Alright, it might be a good idea now to kind of give names to these things. So now if I go ahead and run this, I can click on these scopes, and the average waiting time was 0 and the average queue length was 0. Well, let's see what happens if I change the entity server's processing time from 1 to, say, 1.5. And now when I run this, we can see that the waiting time starts to increase, as well as the average queue length starts to increase, kind of out of uncontrollably, because packets are coming in once every clock tick, but they're not leaving once every clock tick. One of the things we can do now is we can change the way that packets are generated. And so, for instance, if I were to go to entity generation, I can change the time source from a dialog to, say, a MATLAB action. And this is any MATLAB code expression. And so this is going to be a random number. Okay, so if I don't want the generation to be so fast, what I can do is simply multiply that by some number. Let's say by 5. So if rand is going to give me 0 to 1, multiply it, it's going to kind of stretch out the time by 5. And so this is actually the time between the next event. This is the delta t, is what that's supposed to represent. Alright, so let's run this thing again, and we'll take a look at our two graphs. Actually, one more statistic might be interesting here, just so that we can see what's happening. We can either generate it here on the FIFO or generate it here on the server. We can go here to statistics, and we can say either the number of entities departed, and maybe we want to see how busy our server is. And so we'll turn on those two statistics, and you guessed it, we'll add 2 more scopes. And again, I'm just going to connect these two, the outputs to the inputs, and let's run these. And now I got scopes all over the place. But we can see this is the average utilization, and this is the number of entities that departed. So let's go and make one more change. And then what we can do here is go to event actions. And here, entity type first. So in event entity type, what I want to do is I want to take this attribute 1 and I'm going to call it processing time. And in processing time or proc time, what we can now do is when we generate the event, I can come in here now and say, let's click on insert pattern. We'll do random number. And so what MATLAB has done here is it's generated a bunch of code, probably way more than I would have. But it generates a random seed. It generates a, this is the kind of bandwidth of an exponential function. It's going to generate that function and store it in x. And so this is going to, again, be between 0 and 1. That's what that moo means. So let's make that moo be 2. So that'll be our processing time. And then we can say entity.proc time is equal to moo. All right, so now whenever an entity is being generated, it's going to generate how much time it should spend on this server. And over here in this server, and when I say how much time does it take on that server, I want to do an attribute, and the attribute is going to be proc time. Now, when I go to run this model, we can start to see that the processing time is kind of randomly happening. So let's bring up these other two scopes. The utilization is, we're starting to get overwhelmed here. I'm sorry, this is utilization. So we're always busy, and then at the very end we kind of fall off. So apparently there was not an event right there. So we're still kind of like generating more events than what the server can handle. So let's go back one more time to our event generation. And instead of generating an event every 5, let's double that and make it, we might generate a few events, but we may only generate one event in this in 10 seconds or 10 units of time. And so now if I run this thing one last time, look, we see that we actually only generated a couple of events, and the average queue time was 0.
Finally, we can take a look at Cisco Packet Tracer. I should comment that I've kind of horked this video from the Cisco Network Academy, and the guy who does the presentations just kind of is really enthusiastic. I definitely, I guess, admire that level of enthusiasm. You'll see what I mean.
Hello, everyone.
Okay, so those tools were really interesting. I hope you have a chance to download and explore them on your own. It is definitely time well spent. And we'll do some labs with those later on. Like I said, this is just introductory material, and so we'll get there. Shifting gears a little bit, we can start to talk about internet service providers. The internet is a network of networks. That's kind of the definition that we've been giving it. And to make it all work, networks need points of contacts where they can exchange data from one to another. And we call these points of contact Internet Exchange Points, or IXPs. By design, access to these global scale IXPs is limited to just the top networks to hand off data between each other. The same strategy can be replicated regionally, where Tier 2 ISPs exchange data with each other in that region, and with the Tier 1s, who might also have, some of the Tier 1s will certainly have presence in some of those Tier 2 IXPs. The strategy then is replicated more locally, where local ISPs exchange data with the Tier 2 ISPs, and so on and so forth. We'll see soon that large companies may opt to skip layers of the network to gain better access to particular markets for their products, and they will maintain what's called a point of presence on a particular network. For example, if Netflix determined that the local customers of some ISP in a region could not really gain access to their service efficiently, Netflix might actually work with that ISP to have a point of presence at that network exchange. Tier 1 providers are the largest internet carriers in the world, and some of these represent some of the biggest telecom companies in the world. There are only about 15 of them, but their networks span literally to every continent. The Tier 1 IXPs exchange data between themselves, and access to these peerage sites is exclusive and expensive. And as I said, its members represent the largest telecoms in the world. By agreement, these companies don't charge each other for passing off of data. They share the costs of running these IXPs, and they give each other equal access to each other's networks. Of course, they don't do this out of the kindness and generosity of their own hearts. Instead, they will turn around and use this as revenue generating for the Tier 2 ISPs and the companies that try to establish their own points of presence. To get an idea of how big one of these ISPs can be, take a look at AT&T, headquartered here in the United States. AT&T used to be the phone company, and they have to date 410,000 miles of fiber optics that they manage as part of their Tier 1 network operations. CenturyLink, formerly Level 3, L3 Communications, to this day, I believe, they don't exist as a company, but they did a lot of government contracts and things like that. They maintain 750,000 miles of fiber optics. So it's hard to imagine how any smaller player would be able to compete against such huge, well-established companies. Internet exchange points are where these Tier 1 providers meet the rest of us rabble. There are about 100 of these facilities throughout the world, some huge ones, such as this facility in New York City. Others are smaller and more regional. Most handle thousands of gigabits per second or terabits per second. Some hundreds or even thousands of terabits per second. It's just mind-bogglingly fast. Many of these also are handing off telephone and other wireless communications, and so these hubs are just large communication hubs, not just for internet traffic. Unfortunately, detailed information about these exchanges is hard to find, especially after 9/11. These physical locations are as important to our modern society as gasoline reserves and power stations are. And many of these buildings are actually hardened physical structures against the kinds of attacks that we've seen from terrorists or even potential government warfare type attacks. So let's take a look at this short video. I have an example here of some statistics I was able to find about one of the largest network access points or internet exchanges in the country. This is Verizon's network access point of the Americas. It is a 750,000 square foot data center located in Miami, Florida, with 125,000 square feet dedicated to the U.S. government. There are 7 Tier 1 providers that are co-located at that facility, with 160 Tier 2 network carriers representing 148 different countries, all maintaining a presence within this facility. If you were a company that wanted to participate in the network meetup that happens here, they require that you maintain at least an OC48 connection to the facility. And we know how much that, well, we can estimate how much that costs. I mean, you're looking at $10,000 to $20,000 a month just for the local loop of an OC48. So to participate in this facility is gonna, you can easily imagine, is going to be millions and millions and millions of dollars a year. The facility itself is a hardened physical building. It is designed to survive a direct strike by a Category 5 hurricane and to survive a 100-year flood. It was located in a 500-year floodplain, and so theoretically it can sustain some pretty significant damage. Its walls are 7-inch thick steel reinforced concrete. The cooling system is 5 systems, each with 2,000 tons of chilled water, all redundant on top of each other. These data centers generate tons of heat. And of course, Florida is already a hot zone. And so air conditioning these systems is of vital importance. The non-federal government part of the facility maintains a 24-hour armed guard security. We can only imagine then what the federal government maintains. The only data I could find is that this facility is the central communications for all of the U.S. State Department. So all the classified, extremely sensitive diplomatic communications for the U.S. foreign operations and the Foreign Service all go through this one facility. Power to this building has to come from two different utility grids. And so they have two 13,200 volt feeds that power this facility, as well as their own on-site generators with guaranteed gasoline reserves. I mean, these facilities are just crazy in their design and redundancy, and being able to have your data system and your network connections live in these facilities is certainly not going to come cheap. If you're a Tier 2 provider, you will peer with other Tier 2s, and there may be costs associated with that depending on the scale of the Tier 2. Or it may just be by agreement that you agree to share data with each other. But you're going to end up having to pay for transit for data that goes out over a Tier 1 provider. And so depending on the cost, that's going to determine how you route data for your customers. Again, it may be that if you have a choice of Tier 1 providers, some of your customers who pay more money may have their traffic routed to a faster but more expensive Tier 1 provider. The decisions that get made on how you route your customers' data can cost money, and you're going to need to recover those costs. Tier 2 providers are going to resell access to their network to Tier 3 providers and to other points of presence, and they may even do it directly to their own customers. So, for instance, Comcast, their network is actually a Tier 2 network, and they are one of the largest internet service providers in the world. But then you look at CenturyLink, not the Tier 1 big backbone company, but the franchise of CenturyLink that does DSL service. And those are all very regional groupings that tend to be listed as Tier 3s. Also in this list, you'll see the national telecoms. So even in these top lists here, we see like Korea Telecom, China Telecom, the Deutsche Telekom, all of these different kind of national groupings are going to be Tier 2s. Unfortunately, when the internet was originally conceived, nobody could have envisioned the massive global services such as Google, Netflix, and Facebook. In 2018, Netflix alone accounted for 15% of the total global internet traffic. When the global pandemic shut down much of the world, Netflix had well, they didn't have to, but they voluntarily disabled HD streaming because so many people were at home streaming that the regional internets were unable to handle demand. For these companies' services to scale up to meet global demand, they have had to change the rules of the internet. For example, Google maintains its own global TCP/IP network, at times leasing dark fiber from the Tier 1 providers, at other times installing their own. With their own global network, Google is then able to participate directly with Tier 1 providers at the internet exchange points and deliver content faster and more reliably to users. In other words, Google has opted to do their own network and try to take as many of the middlemen between you and them out of the picture. Netflix, on the other hand, has taken a different strategy, offering internet service providers access to a tool they call OpenConnect, which are effectively content servers that the ISPs can install on their own networks. When a subscriber of that ISP starts to stream a movie, instead of having it come from Netflix's central servers wherever in the world they are, it is served right from the local Netflix content server. leaving the more limited upstream network connections for that ISP free for other subscribers. My understanding was that either Shippensburg University or our direct provider installed a content service because of our residence halls. I'll try to find that out. I'm going to try to invite our network engineers to come in, and that can be a question that we can ask them, how they handle that. So imagine what it would take to launch your own competitor to Netflix today. This is clearly beyond the realms of possibility for most of us. I mean, there's no way that we're going to be able to very quickly go to the 5,000 different ISPs that are in America and say, hey, can we install a server in your server room so the customers that we don't have yet will have a really good experience for our product that doesn't exist yet. I mean, you're just not going to be able to do that. So, I mean, it just feels like now the days of, a couple guys innovating something new in their mom's garage are kind of over. And maybe that's okay. I mean, I kind of like having the services that we have, but it's also, kind of a dysfunctional world if nothing new ever comes about. One of the key things, if we're going to talk about an introduction to networking, we've got to talk about this idea of what's called encapsulation. And this is an area of computer science that we will see over and over and over and over again. And it's probably one of the best examples happens here in networking. So throughout this lecture, we've talked about protocols, things like Ethernet, which delivers data in frames across local wires, or Wi-Fi, which delivers frames of data through the air. We've also talked about the Internet Protocol, which can be used to send, route, and receive packets between distant machines. But IP packets don't just leave my machine and magically on unicorns and rainbows end up somewhere else. Instead, IP packets are wrapped, they're encapsulated, they're embedded into an Ethernet or Wi-Fi frame. And then that next level down, the Ethernet card or the Wi-Fi router, they deliver locally to the next device. And then the Ethernet frame doesn't care what it's sending. The Ethernet frame is like, oh, I've got to send 86 bytes, so I'll wrap it with my information, so if you're paying attention to Ethernet, you see what I'm sending, and then we'll send those bytes. And so this strategy allows multiple protocols to live on top of a lower level. So for example, if I'm using Ethernet, I don't just have to use IP, I could use other protocols as well. If I'm using the IP protocol, I don't have to just use TCP. I could use UDP or any of the other transport layer protocols. So each of these different layers guarantees a certain level of independence from the layer above and below. And if I'm designing something at one of these layers, I can kind of ignore the layers above and below. I can let the interface between the two deal with anything that needs to happen. So for example, an IP packet can be bigger than a an IP packet can be bigger than an Ethernet frame. And so if that's the case, I have to take, and when I hand off the IP packet to the link layer, I'll have to split it up into multiple frames. So the textbook goes into a really nice description of the fact that we have two different versions of this protocol stack. The 5-layer model is kind of what engineers actually use, network engineers. Whereas the 7-layer is really the official academic, like if we're going to be really spot on, true to the science, we really should use the 7-layer model. We'll find out exactly why that is when we talk about that application layer, and it's really a pretty clear reason why. So if each layer is going to deal with a different representation, what do these layers represent? So at the application layer, we're talking about things like an email message or a web page. At that transport layer, where we have instructions of how to deliver data once it's received by a system. So, for example, you can have multiple web pages open to the same remote web browser, and somehow the network has to keep each of those web pages separate from each other. And that's going to actually happen at that transport layer. Network has the instructions to deliver data between systems, and so this is going to be the IP data that's going to say, oh, this data packet belongs, send it over to Google, this one goes to Millersville or wherever the remote system is. The link layer is going to have instructions to deliver data between devices, and so this is going to be things like Ethernet. Here's an Ethernet frame and I'm going to send it to my printer. Here's a different Ethernet frame. It's going to go to my router. And at that physical level, we really are dealing with electrical signaling. So let's go into a little bit more detail one more time on these. Layer 1 is the physical layer, and it deals with the mechanics of getting a digital bit from one location to another. At this layer, we are talking about data link frames, or we're taking data link frames and turning them into voltage differences on a wire, or disturbances in the electromagnetic spectrum, if it's a wireless device, or bursts of light over fiber optic. At the receiver, we're detecting these signals, whatever they are, and we're turning them back into digital data, into what will become link frames. And while Ethernet is certainly the most standard physical layer mechanism, and there are many different forms of Ethernet. There's the 10 base T, 100 base T, gigabit, all kinds of different Ethernet standards. But there's also Bluetooth, Wi-Fi, USB, CAN bus, all different types of ways of getting a frame of data from one system to another. Layer 2, the second layer, is the data link layer. And data link layer deals with frames and takes the network data and turns it into physical frames that can then be handed to a device for transmission. So, for example, the data link layer will take an IP message, which is bound for some remote system, and put it into an Ethernet frame that can be put onto the Ethernet link, but with instructions to send it to the router. Now, the local machine doesn't have any idea how the router is going to get it to Google, but it knows that it can say, here router, this packet is not for any local machine, it's remote, go deal with it. At layer 3, we have the network layer, and this has the responsibility of getting data from one computer to another, without respect of whether it's local or not. And so when I'm creating a network request, we call them, when we look at these, we'll learn to call them sockets. If I open a socket and throw some data down, I'm not going to say, hey, to the socket, this is local or this is remote. I'm just going to say, here's the data. And so at the network layer, we're going to be producing packets, and those packets are going to hold the information that I need to get it from one local system, my local system, to some other system. Maybe it's remote, maybe it's on my LAN. Maybe it doesn't even exist. It could be an error. But at this point in time, we don't know that yet. The transport layer is responsible for taking application data directly from a program and going from one computer and getting it to another program on a different computer. And so the transport layer is going to have things like an address of the program within the local machine and the address of a different program on the remote machine. We'll call those socket endpoint numbers. And that's how we can have, say, two different connections to the same machine and keep the two different connections unique. The transport layer operates in segments or datagrams, and we're going to expect reliable transmission of those segments or datagrams between different computers. However they get there, we don't know or care. We just know that at some point the data gets there reliably. The classic examples of these are going to be the TCP and UDP protocols, which we'll look at in a later chapter. And finally, we get to the application layer, whether it be layer 5 in the 5-layer model or layers 5, 6, and 7 in the application model. In the let's talk about what they are and how they look. So at the protocol data unit for the application layer is just data, and that data could look differently depending on what it is that we're trying to exchange. Layer 5 in the 7-layer model is all about managing communication sessions. Layer 6 is all about translation of data between the network service and the kind of higher level application. And layer 7 is going to be the high-level APIs, the resource sharing, the remote file access, or whatever the kind of user-visible function that we would expect. So I tried to think of a good example for this, and I think that the Secure Shell protocol is probably one that you're mostly familiar with. And if you're, well, let's assume that you are, and if you're not, oops. At the top layer, you type in some keys and magic happens and they get out to Sloop or whatever the remote server is. And so at the very top level, that OSI level 7, the SSH protocol emulates a remote terminal. So you SSH into a machine and it looks like you've connected to the terminal directly. That's layer 7. Layer 6 has the job of taking the data that you've typed and kind of wrapping that into an SSH message and encrypting it and maybe even compressing it so that you're not sending as much data across the wire to be more efficient. Layer 5 is all about what we call the keep alive protocol. So when you are sitting there at Sloop and you're trying to write some code and you're stumped and so you're just staring at the screen for an hour and a half, Sloop knows that you're still sitting there, that you haven't lost your connection, that you haven't ended, you haven't quit, you haven't logged off. So we call that keep alive protocol. And if I were to design my own SSH program, I would write something at layer 5 that just periodically sent a ping that says, hey man, still alive, still here, it's all okay. But that has nothing to do with you interacting with the SSH terminal. It has everything to do with SSH kind of making you think that this is how it works. But if we were to implement it, we would need to have these 3 different layers of communication. Now, the reason why OSI does this is because this is really important for an application developer. If you're a software engineer, you're probably going to spend most of your time dealing with layers 5, 6, and 7, and a little bit of your time dealing with layer 4. Probably nothing else. On the other hand, if you're a network engineer, you're going to spend all of your time on layer 1, 2, and 3, maybe a little bit of 4, and you really don't care about 5, 6, and 7 unless the software is just so poorly written that you need to give the software engineers some help. So if your main focus is on network engineering, you typically just ignore 5, 6, and 7 almost completely, lump them all together as one layer, and there we get the 5-layer model. So it's just a simplification and almost like a intentional ignorance of what's going on in some of these applications. So, as I said before, encapsulation is a really important concept, and it's important to note that each layer in this kind of layer cake will wrap the data from a higher layer with its own layer-specific envelope. And then once it's received, as the data is coming back out, as the lower layer gives the data back up to the upper layer, it unwraps its specific layer so that the data layer above it sees just what it expects. So if I were to have a wireless and an Ethernet connected link layer, and I got an IP message from a remote computer on the wireless, and then I got one on the wired, by the time the link layers took off their lower level stuff, the IP messages would look exactly the same. So there'd be no residue of how they were received in the IP kernel. It would just be, oh, here's an IP message, I know what to do with it, I'll give it to this TCP connection. To make this happen and to be consistent, we have the rules that layers can't be skipped, and the layers can't do anything with data from another layer. So, for example, an Ethernet switch will never pay attention to IP packets, or at least it shouldn't, because not all Ethernet frames are IP packets, and not all IP packets will end up as Ethernet frames. But by treating each layer as separate layers, it allows us to make decisions about the data at each layer along the way. So it really kind of gives you the best of all worlds, and as long as you play by the rules, it very seldom will get in your way. Finally, history is always important, and one of the advantages that we now have is that many of the founders in network technology are still alive, and they're fortunately very willing to give interviews and make recordings for posterity. So for us to be able to see a big guy like Vint Cerf give an interview would be like for a physicist being able to talk with Isaac Newton. We should really take advantage of it. So instead of me going on about the history as the textbook does, I've got a video here for you to watch. It's about 50 minutes, so I'm not going to inject it into these lectures. But I think if you watch it, it'll help kind of raise your perspective about where all of this stuff has come from. And I think you'll be surprised about how many of the terms in the video you are suddenly now familiar with, that you've seen before. And in fact, I think if you look at the very first parts of the video, you'll even recognize the facility that the guys are in when they talk about the Internet Exchange Point. I'm pretty confident they're in the Hudson Street in New York. So I think this finishes the lectures for Chapter 1. Congratulations for surviving this far. And I hope throughout this that you are taking good notes, you're asking good questions. If things remain unclear, please talk to me, either in class or in office hours, and let's try to get those questions answered. So thanks a lot, and I'll see you in class or in Chapter 2.